We're going to study another reaction that happens with aldehydes and ketone, and that is a Baeyer Villiger oxidation. This reaction uses peroxy acids. So first, let's say what is a peroxy acid. So you have, say, for example, acetic acid, and you will abbreviate it like this. Well, let's say CH3 CO2H, acetic acid. If you add one more oxygen, you have a peroxy acid. So in the peroxy acid, you have the following. This is peroxyacetic acid, and it will be CO3H. So peroxyacetic acid. This is what we're using in the Baeyer Villiger oxidation, a peroxy acid. One common reagent that you will see is metachloropurbenzoic acid, abbreviated as this. The structure is, let's draw benzoic acid first. So benzoic acid is this. And if I say metachloro, it's this. But now it is a per acid, so I'm gonna have the following. So that is metachloropurbenzoic acid. So likely you will see this, and you need to know what it does. So what it does to aldehydes and ketones, this is what we are studying next. If we have, this is a ketone, what the peroxy acid does, so I'm going to do R and 3 oxygens, right? RCO3H is my peroxy acid in general. What it does is inserts an oxygen in between the carbonyl carbon and the one next to it. So I'm going to, in this case, expand the ring by inserting that oxygen. So here, notice I have 5 carbons, and I have 1, 2, 3, 4, 5. But the ring is now 6-member ring since we have inserted an oxygen. Since the ketone here is symmetric, doesn't matter where you put the O, on the side or the other side. But when it's not the case, when we have a carbonyl group that has different things on different sides, then what we need to study is what is the aptitude to migrate. The reaction involves a rearrangement, a migration of a group, an alkyl group, or an H, or a phenyl maybe. So what we need to know is what is easier to migrate. So we have an order of the migration aptitude, and I'm going to write it here. Hydrogens rearrange, they migrate better than tertiary carbon, and those better than secondary. And that is about the same as the phenyl. And then we have the primary, and lastly, the metal. So that means these migrate faster. So let's do an example with this. If I had, now let's do an unsymmetrical carbonyl compound. This was symmetrical. Let's see. Now I have a carbonyl. I'm going to draw an aldehyde, so acetaldehyde. So this carbon is primary, that is a hydrogen. If you put that with, say, metachloropurbenzoic acid, markers, okay. So NCPBA, that a per acid. So I need to decide where is that I am inserting the O. So the aptitude for migration, the largest one is the migration is faster, is for the hydrogen. So I'm going to insert the O on the side. And what it is we're making a carboxylic acid. So aldehydes, because they have a hydrogen, they always make a carboxylic acid. Because again, the hydrogen has the greater, say, migration aptitude. So let's go for another structure. Asymmetrical, we know it's not a problem. So I'm gonna erase that and do some more examples. So I gotta have now, let's see. I'm gonna put a metal on one side, and on the other side, I'm gonna do like isopropyl. So here we have, that is a primary carbon, and that is secondary. So if we check out the migration aptitude, is better the secondary one. So what we're gonna form, we're gonna insert the oxygen on that side. So say a peracid, CO3H, and now I am forming, inserting the O again on this side, that, and you're gonna make an ester. So when you're moving alkyl groups, you're gonna make esters. Now let's look at something else. Say that I have, that compound is acetophenone. And in this case, we will see that is a primary carbon, and that is a phenyl. And as we can see, the phenyl migrates, has a better migration aptitude. So let's write metachlorobenzoic acid. So what I need to know is that precisely, the migration, that's better. So I'm going to form the ester on that side. So let's say this is acetophenone, and this is a phenyl acetate. So we're forming also an ester. The name of that is phenyl acetate. Okay, so that's all we need to remember for the Baeyer Villiger oxidation. Remember that structure, metachlorobenzoic. Remember that when you have an extra oxygen, is a peracid, in that the reaction that you will be doing is inserting an oxygen. Where do you insert it? Then keep in mind that's what you just said is the migration aptitude. The reaction involves a rearrangement, the migration of a group. So you need to know what migrates better. That's the fastest. So always, aldehydes will give you carboxylic acid. Ketones, you need to decide where do you put the oxygen, but you will make esters. They're gonna make another one more. Well, we did that example at the beginning, I believe. So I didn't just say the name of the compound. When you have a cyclic ketone, as we had at the beginning, I had cyclopentanone in the first example that I had. And here the molecule is symmetrical, so doesn't matter where I put the oxygen, we're gonna make the same ester. So here I'm gonna do RCO3H, and I will be inserting the O to one of the sides. And notice there is a ring expansion. That is a cyclic ester, and this we call lactone. Not functional group, it's simply an ester, right? But it's in a cyclic form, lactone. Now, the cyclic ketone can also be unsymmetrical, and I can make it unsymmetrical here. Just I'm gonna add a substituent. And now, specifically, you need to insert the oxygen. There is a place that's preferred. If you see this carbon, that has 3 bonds to other carbons, so that's tertiary, and that is secondary. So the migration is better to that side, see, tertiary. So now I need to put the O over that side. So RCO3H. I'm gonna make another lactone, but I must have it on this side. Again, it's a 6-member ring, but I will have this metal. So here, it doesn't matter to what side I insert the oxygen. Here it does. So the degree of substitution will tell you what is the product that you need to rewrite.